The smaller the value of your alpha, like I said, the stronger we require the evidence to be in order to reject the null hypothesis. So in the SAT example, at a significance level of 5%, we reject the null hypothesis. If we said that alpha was 0.01, we would have rejected the null hypothesis only if the test statistic had been in the most extreme 1% of the distribution. So if we reject the null hypothesis after choosing a significance level, we say the result is statistically significant at that alpha level. So when we rejected up here at 5%, we said that the result is statistically significant at 5%. And when we talk about things being statistically significant, we basically means in that alpha, that critical region for whatever alpha is. So the critical region for your hypothesis test is going to be dependent on if we're doing a left tail, right tail, or two tail test. So if we do a left tail test, so remember left tail is if we're looking at a less than. So let's say our null hypothesis was at 100, then the alternative hypothesis would have to be your mean is less than 100. So that means our critical region goes to the left. So if alpha is 5%, then there's 5% in this critical region. The one that we had done was a right tail test. So that would be the case if your null hypothesis was the mean was 100, then your alternative, and I just realized I used the wrong alternative. So H1, my alternate hypothesis, H1. In this case, it would have to be greater than 100. Now, if you have a two-tail test, what happens is where we have alpha is solely in this tail or solely in this tail. So like I said, if alpha is 5% for all of these, then that means there is 5% here. That means there is 5% here. But the two-tail test, that gets split in two. So we don't have 5% in each tail. We have 2.5% in that case. But this is the case where if the null hypothesis was the mean was 100, then the alternate hypothesis would be that whatever it is, it's just not 100. So it could be in the left tail, it could be in the right tail. But we still want that significance level of 5%, so we just split it between both tails. This table indicates critical values for some commonly used alphas. So we've experienced some of this before. So we know that when we talk about a distribution, this z-score and this z-score are going to be equal to each other, especially if they have the same alpha here and here. So things we found out before, if we have 10% in the tail, then the z-score, if it's in the left tail, is going to be negative 1.282, but in the right tail, it's 2.282. For 5%, left tail is negative 1.645, but right tail is positive 1.645. So you see, like I said, it's that because of that symmetry. At a significance level of 2%, then the z-score would be negative 2.054 or positive 2.504 for the right tail. At 1%, the left tail is negative 2.326, and the right tail is 2.326. Now, when we talk about a two-tail test, we're getting half of that alpha in both tails. So we're going to still get a z-score, but we're going to have look at a positive and a negative z-score. So for a two-tail test, 10% is going to be plus or minus 1.645. 5% is plus or minus 1.96. 2% is going to be plus or minus 2.326, and 1% is going to be plus or minus 2.576. And you should recognize these from confidence intervals. Because we're talking about those confidence levels, this is 90% level of confidence, 95% level of confidence, 98, and 99. So assumptions, we always have assumptions that we have to technically test. The assumptions for performing a hypothesis test about mu when sigma is known is we have a simple random sample. So we usually assume that's what's happening. And we assume that the sample size is larger than 30. Once again, because of the central limit theorem tells me that if it is, then my population of means is going to be approximately normal. However, the population itself, if x value is approximately normal, then the distribution of my means should also be approximately normal. So we're going to do a test here. So the American Automobile Association reported that the mean price of gasoline of the mean price of a gallon, sorry, I read that wrong, a gallon of regular gasoline in the city of Los Angeles in 2019 was $4.07. And I can believe that. It's a lot more expensive out in California. We're going to make our hypothesis here in a second. So let's get ready for that. So the claim from the city of Los Angeles is that the mean price is 4.07. A recent random sample of 50 gas stations had an average price of 4.02. Assume that the standard deviation of prices is 0.15. So it's not safe from a sample. We're just assuming that that is for the population. And economics is interested in determining whether the mean price of gas is actually less than 4.07. So our claim, mean is less than 4.07. So that's my hypothesis test. So we want to perform a hypothesis test at an alpha level of 0.05. So we're looking at, this is what is normally going on. They're claiming that gas is actually less than the claim. So this is a left tail test. Right, so we need to find a couple things here. One is we need two different z-scores. We need z-score for our population mean. This is my test statistic. And then we also need the z-score for the query to the critical region. Which in that case, that means I need to figure out a z-score for 0.05 in the left tail. So we're saying that this boundary right here, that what we expect to be here is 0.05. Okay. So if we go back to our chart here quickly, left tail, we have a 5%. That z-score is going to be negative 1.645. So this is that z-score for that alpha level, and that is my negative 1.645. So this one here, we just need to figure out the z-score. And what we need to do is take the mean from the sample, subtract the mean from our hypothesis test, and then divide by sigma, which is divided by the square root of n. So for us, it's going to be 4.02, because that is what is claimed from the sample. Let me write that again, because that was a little sloppy. 4.02 minus what is claimed in the hypothesis test, which is 4.07, divided by my standard deviation. Sorry, put it over here. A standard deviation of all gasoline for the whole population is 0.15, and then we divide this by the square root of the sample size, which is 50. So don't forget to use parentheses to make sure that everything stays where it's supposed to when you calculate this. So we're going to have 4.02 minus 4.07 divided by parentheses 0.015, which is then divided by the square root of 50. Close my parentheses in the bottom. So I got an extra zero somewhere. I got a really crazy score. This is negative 2.3. We'll go 3.6. We only need to go 2 scores for the most part. So let me draw my little image again, make it a little bigger. So here's my distribution. It is centered at 4.07. Oops. We are doing a left tail test, so my critical region is here. And we see this area represents 0.05, so 5% of everything should be in there. So the z-score for this boundary is negative 1.645. So the one that we have right here, we have to decide where that goes. Is it in my critical region? Well, negative 2.36 is inside the critical region. So remember, if we're in the critical region, what that means type this up here. So we're in the critical region. So Z equals negative 2.36 is in the critical region. If we're in the critical region, that means we reject the null hypothesis. We reject the null hypothesis. So that means if we reject the null hypothesis, we have evidence to support the claim that gasoline is less than $4.17 per gallon. So basically we're saying that null hypothesis is true. So that is why we use those critical regions, because we're in that critical region, we are so far away. This score here is so far away from 4.0 or 4.07. This, if you remember, grab another color, this here is representing the 4.02, which we got from the sample. So it's saying that the sample is telling me that it is so distant from the null hypothesis claim that it can't be simply due to random chance. It's not actually close to the null hypothesis mean. It is too far away. It is too small, is what it is. It is so small that it just supports our claim that gasoline is actually less than $4.07 a gallon. So some studies suggest that regular meditation can raise a person's intelligence. So this was brought up before in another problem. We know that the mean IQ of all people, whether they meditate or not, is 100. So null hypothesis, we know the IQ is supposed to be just 100. It's 100 with a standard deviation of 15. So we know sigma is 15 because that's all from the population data. Researchers gather a sample of 50 individuals who regularly meditate and found that their mean IQ score, so from the sample, is actually 103. So it is a little higher, but is it high enough to be weird? We will perform a hypothesis test at an alpha level of 0.05 to support this claim. So going back and figuring out what our alternative hypothesis is, studies suggest that regular meditation can raise a person's IQ. Meaning that if it's not 100, what we expect is that it should be over 100. So we are going to run through this problem again, as you see here, because we're going to perform this hypothesis test at a sample size of 50. So we already kind of did this once before, but we know that if alpha is 0.05, we know that we have a right tail test. And we know it's a right tail test because we're looking for a mean that's higher than 100. And hundreds should be here. So the z-score that's going to mark that boundary for me, if you went back to your chart, we already used this once before, but it's 1.645. So that is the boundary to get into that critical region. So our first part, if we're looking at a sample size of 50, then my test statistic is going to be the z-score for x bar minus mu divided by sigma, which is then divided by the square root of the sample size. So our sample we collected had a mean of 100. This hypothesis test tells us that what we expect is that it's really just 100, because that is just the claim. Well, it's not 103. What it should be is really just be 100. The standard deviation of all IQs is 15 divided by the square root of my sample size, which is 50. So once again, put this all in the calculator. We are going to have 103 minus 100, close parentheses, divided by other parentheses, 15 divided by the square root of 50, close my parentheses, and I get a z-score of 1.414. So where's this z-score set? 1.414. It is not in the critical region. So if I am not in the critical region, that means, like I said, the critical region is the rejection region. I'm not in the rejection region, so I cannot reject. We fail to reject. We do not have evidence that meditation causes an increase in IQ. We do not have evidence that meditation raises IQ. All right, so what we're saying is that if I take a sample of size 50, then it's likely that with a sample of size 50, they get a mean of 103. That is likely just simply due to chance. Like I said, I'm going to collect several samples of size 50. most of them should be centered around 100. I'm collecting one sample that comes from those who meditate, and this one is close to 100, just like any other sample would be. This could simply just be random chance that I get 103. It does not indicate the IQ has raised. So the second part of this, we will perform this hypothesis test again with a sample size of 100. So when I do my test statistic, let me pick a new color here. Just because I already wrote in blue and we don't want too much blue on here. My sample size is 100 now. I'm finding my test statistic. So I'm finding that z-score. So that's a z-score, once again, of 103, subtract 100, divided by a standard deviation of 15, which is divided by square root of not 50 this time, but 100. So this one comes out exactly to 2. Now 2, however, 2 is in the critical region. So this is in the critical region. We reject the null hypothesis. So we reject the claim that IQ is actually 100 for this group of people. So this is claiming that people who meditate have the same IQ as everyone else. And we're saying, nope, that is wrong now. We have evidence. We have evidence that meditation raises IQ. So because we collected a bigger sample of size 100, what that means is that because the sample size is bigger, it's less likely that 100 people would have an average IQ of 103. So every time we make that sample size bigger, what we're seeing is our probabilities decrease is what's happening. Because we're, like I said, an individual, if I collected one individual who meditates, like I could expect that their IQ could be, like 180, not 180, I'm sorry. I can expect it to be 80. I can expect it to be 120. All of those are reasonable because one person could be all over the place. However, we don't expect a whole group of people to be all over the place. When we do groups, we expect it to get closer and closer and closer to the mean, right? So bigger sample sizes should have means that are closer to 100. So when they're not, the probability that they're not going to be close to 100 goes down over time. So sometimes if we want to make sure that our hypothesis test is true, not only can we increase or decrease our alpha and make the test harder, we can also take larger sample sizes because larger sample sizes may actually put us in that critical region or they may not. But like I said, this is just a difference here. If I did a sample size at 50, I reject the null hypothesis. I failed to reject the null hypothesis, but at a sample size 100, I do reject the null hypothesis. So sample size can have an effect on that.